Just a little recapitulation since you weren't here last time, although I'm thinking you've watched some of the video, at least maybe enough to see this. But just putting it together, because you mentioned you had a little trouble if you got a bunch of masses. Okay? Very simple. It's as simple as you would hope that it is. Yeah, I was looking at something that didn't look right. Okay. So if you got a mass, m sub I, one of many masses. You know, looking at the system, we got all those magnets. I pointed the magnet, asked you to tell me how to get the kinetic energy, and you were able to do it. And that's what leads to this. So you got mass m sub I, distance r sub I from the system, angular velocity omega. There is your kinetic energy, just same reasoning you used for your estimate. We write that as 1/2 I sub I omega squared. Okay? I, sir. Okay? And I sub I is what we call the moment of inertia of that mass. Okay? Now that magnet is not a point mass. This would have to be a point or point-like mass. We're treating it as if it's a point-like mass. Okay, there are little errors we make if we do that, and once we do the integration and everything, we see where those errors come from because of the nonlinearity of this effect with distance. Okay, so the middle of the magnet is not at the middle of the r squareds for all the particles in the magnet. Okay, and if you understood that, fine. If not, we'll come back to it later anyway. Okay, well, that's one of the magnets. Now, you can make, how many magnets are there? 1, 2, 3, 4, 5, 6 magnets? Yeah. Should be one hanging on the other side there. I can't see it, but it's got to be there. So there are 6 magnets. So you can make the same estimate for every magnet, right? You get some different results because you got different R's, meaning they're going faster. But you could easily do that. So what would you do to get the total moment of inertia? Or the total kinetic energy?
Add up the kinetic energy involved.
Yeah, so what would you do to get the total moment of inertia?
Add up the individual moments of inertia.
Okay, so it's a sum of the kinetic energies, and that clearly equals same omega for every one. And since it's the same omega for every one, and since 1/2 is constant, the 1/2 and the omega are constant, so they can factor out of the sum. So that's this, where I is the sum of the I sub I, the sum of the moments of inertia of the particle. Okay? Now, in that system, they're on the order of 10 to the 22nd particles. Okay? 2 times 10 to the 22nd, something like that. Actually, maybe even 3 times 10 to the 22nd. So, you know, this sum would get really big. But we can treat each magnet as a continuous solid. We can treat the beam as a continuous solid. We can treat the straps as continuous solids. And use integration so we don't have to add up 3 times 10 to the 24th tiny moments of inertia. Okay? For now, we're just going to sit with discrete systems, okay? If we analyze this system, I'll just kind of tell you what the moment of inertia, I'll give you a formula, okay? Your book gives you a formula for the moment of inertia. Because we're in first semester and we're officially not knowledgeable enough to use calculus at this point. 173, first semester calculus is the only prerequisite, okay? Even though you guys are both okay with integration, I think. If you understand this, then the integration is just window dressing, okay? So that's your moment of inertia. Now, the other thing I was going to talk about today is torque. So you know, if we have this beam here, this is the top view of the beam, with the axis here, axis of rotation, we're looking down on it, and we exert a force here, and this force is perpendicular to the vector from the axis of rotation to the point at which it's applied, okay? And this force is a vector. This vector is what we call the position vector, and we use R for the position vector. We've used R for position vector in projectile motion, okay? And analyze things in terms of the position vector. Okay. Wouldn't have been incorrect if I'd have written FR. I want to write RF. Because the SI units of F are newtons and the SI units of R are meters. So if I write it FR, then the torque is in units of Newton meters, which is like joules. Whereas if I write RF, it's in meter newtons, which is a unit of torque. And you want to kind of do that. You don't want to write torque units as Newton meters because you could accidentally write that as joules. If you write meter newtons, you're less likely to do it. The units are identical, actually, but they have totally different meanings. Okay? The vector torque, incidentally, is a cross product of R and F. And if you don't know about the cross product, take a good look at chapter 1 in your text. It's something you need to know about vectors. Okay? And once you've read that and have questions, I'll tell you more. That's going to become important. Probably not till after next week. Okay, so just sticking with this definition. If F is perpendicular to R, torque is RF. Okay? If F isn't perpendicular, well, it's perpendicular, it's a component of F perpendicular to R. So if F is off in this direction, you got to express it as a sum of vectors in the direction or along the line of R and perpendicular. So you just resolve the vector. And you know, if this angle is theta, then that's just going to be F sine theta. Okay? That's a pretty easy thing to understand. Now, why is this? Okay, the torque equals R times F. Well, okay, I'm going to claim that the net force, I'm just going to tell you the result and then tell you why. Instead of trying to develop common sense, which is what I usually try to do, but let's try this approach. W net equals, well, actually, I guess I am going to tell you. it equals F delta X, okay? Except I really want to use S because for distance along an arc, okay? Displacement along an arc. So I'm going to say it's F delta S. Which is F R delta theta. Okay? At least in this situation. In the general situation, we do it a little different. That's a little more sophisticated. So we've got these exercises. Okay? So net work done by the net force if this is the net force in the system is net torque times delta theta. It's not a rigorous derivation, but it's a plausible derivation. Okay? Well, that's one aspect of this. That's how work is related to this thing that we call torque. Okay? The other is angular acceleration is equal to the net torque over moment of inertia. Which is analogous to A equals F net over M. Okay? This tells us that, well, common experience, you take a 2x4, okay? And you grab it at the middle and you turn it. Okay, you can turn it pretty easily. Gives you, there's some resistance, you know. If you try to turn it too fast, you'll burn out your elbows, or you get tired or something, okay? And we should have a 2x4, but I don't want it in here. And if we use it outside, people think we're stick fighting or something. Then the cops come. No, campus police are great guys. They come out and want to play with them. Okay? And they'll have a good time. But, okay, now, if I take one of these, okay, these, and tape them onto the ends of that 2x4, and you do that, what's going to happen?
It's going to get harder.
It's going to get a lot harder, okay? Because each of these has a mass that's, probably half the mass of the 2x4, okay? Now, if I tape these near the center of the 2x4, it's not going to be much harder to move them at all. Okay? Why is that? Well, it's because in order to move the thing, or to accelerate the thing at the same rate, this thing needs a lot more acceleration because it's going to be going a lot faster at the end of that twist than it would if it's in here. Okay? And the parts of the mass that are closer in the center pick up less kinetic energy than the parts of the mass that are equal parts of the mass that are further out. In terms of the beam, obviously the magnets further from the center pick up more kinetic energy when we accelerate the beam. So if we use that rubber band to accelerate the beam, the further I've got those magnets out, the less acceleration we're going to get for the same rubber band force. So if I pull the rubber band back at the same point twice, okay, once with the magnets distributed as they are, and then once with all the magnets out at the ends, okay?
It'll be very different.
It's going to end up with the same energy because the rubber band does the same amount of work if it's at the same length, okay? But it's going to take longer for it to pick up the energy and it's not going to be rotating as fast. Okay? So you want to think about that, think about how that feels. Okay, think of the 2x, in analogy with that, a 2x4 with masses distributed on it, and play around with those masses. Okay? Okay, well, what happens to the moment of inertia if you move the masses further out? Just take the ith mass. What if you move it further out?
Gets larger?
Because you're squaring that distance, right? It's not linear, it's the square of the distance. So that's what makes it harder to move. Let's say try to move the 2x4 like this. Okay? It's going to be a lot harder to do that. I got more mass toward the ends. Moment of inertia is greater. Okay? If I exert the same force, it's going to be a much slower oscillation. It's going to take me longer to get it out to here, longer to get it out to here. My acceleration is going to be less. Okay? So moment of inertia resists acceleration. If I exert the same torque, same forces at the same points, I'll have the same torque. I'll have less acceleration. Just like with the carts. Okay? If you got two carts stacked on each other being accelerated by the same number of paper clips suspended from the pulley, they have less acceleration. There's more resistance to acceleration if you got more mass, the same force. Or if you want the same acceleration, you're going to have to exert more force. If you want the same angular acceleration, you have to exert a greater torque. Okay? There's another way to exert a greater torque. You just grab the thing out here. Then you can get the same acceleration with a greater moment of inertia with using the same forces. Okay? So you kind of want to sort all those relationships out, but there they are. Okay? And the important relationships are that just that after you have the definition of torque, the fact that the work is net torque times your angular displacement, and angular acceleration is just net torque divided by, not mass, but by moment of inertia. It's not divided by mass because it depends where the masses are. Usually this. Okay? Now we're going to try to sort all that out in lab. We're going to be back on this lab Friday. We're going to make more sense out of all of this. But those are the relationships. Kind of be prepared.